Now, what is the point of introducing a new tool altogether? What is the point of pole zero plot analysis? What are we going to do with this? We can infer a lot of the things geometrically from this. See, remember when we said x of s is equal to some numerator polynomial times denominator polynomial. Now, if I want to know the frequency response of a system, let us say I want to compute the frequency response, but for some reason the impulse response does not have a Fourier transform. Then we compute the Laplace transform. This is the Laplace transform of the impulse response. So, if you evaluate this at some s is equal to some j omega, okay, then you find out what happens to the frequency response of this system. So, this is the magnitude of the frequency response evaluated at a particular frequency. Okay. So, you can also evaluate this at some sigma plus j omega. This also still gives you the frequency response of the system, which is decayed by this e power minus sigma t for a particular frequency. Okay. Now, let us say that we are evaluating this at a particular frequency. So, if you just substitute s is equal to j omega and evaluate this value, it tells you what is the frequency response of the system at that particular frequency. So, which is useful. So, from Laplace transform we can get to the frequency response of the system. But the pole zero plot directly tells us very interesting things about how the system behaves. So, let us take the simple RC circuit. Remember, the simple RC circuit had an impulse response e power minus at u of t and its Laplace transform of 1 by s plus a, and its pole was at minus a. And this is j omega axis and this is the sigma axis. Now, we already know that this RC behaves like a low pass filter, but we identified that it behaves like a low pass filter through a lot of analysis. But let us say somebody just gives you this pole zero plot. Just by looking at the pole zero plot, we can say that this is actually a low pass filter. So, how do you compute this magnitude of the frequency response? So, if somebody asks for this, then you compute the magnitude of the numerator and the denominator, right? But this is already factorized in the pole zero plot, which means you can write this as magnitude of s minus beta I and magnitude of s minus alpha I. So, where alpha are the roots of the numerator polynomial, beta are the roots of the denominator polynomial. Okay. So, now if I want to compute this magnitude in the plot geometrically, what do I do? Basically, if I say that I am operating at this frequency, let us say it is some 10 pi. I want to find out how the circuit reacts at 10 pi radians per second. So, for that I need to compute the distance between this pole and the particular point. What is this distance corresponding to? The distance corresponds to s minus beta I, which is evaluated at s is equal to 10 pi. So, that gives me the value of the denominator polynomial. Basically, this is the denominator polynomial. And there are no zeros for this particular example. So, the numerator polynomial is always 1 or some constant. We do not have to worry about it. So, the frequency response can simply be guessed from this pole zero plot. All it says is, as you move away from this pole, the length between the pole and your frequency value. So, as you increase, let us say now you want to evaluate at 100 pi. So, the distance between your pole and 100 pi is larger than the distance between your pole and 10 pi. So, this length is higher. In other words, the value of the denominator polynomial keeps increasing. If the denominator increases, then the entire expression reduces, which means as the frequency increases, then the entire frequency response value comes down. So as you go farther away from the pole, then the frequency response value will become lesser and lesser. Okay. In this case, as you go farther away from the pole, frequency value keeps. So if you try to plot the frequency response, as you go farther away from the pole, it keeps reducing. This is exactly the plot that we got earlier, and from which we said that this is nothing but a low pass filter. And at 0, that's the maximum gain that you will get. Everywhere else, you will get a lower gain. So this is like a low pass filter. So just by looking at the pole 0 plot, you can tell if it is a low pass filter or a high pass filter. So if there was a 0 somewhere, let us say that there was a 0 here. So as you go closer to the 0, then once again the same thing happens, because as you go closer to the 0, the numerator value reduces. So let us say there was a 0 at this point. So if there was a 0 at this point, then how would we evaluate now the frequency response? Now the frequency response would be this length. Let us call this length L1. Let us call this length as some R1. Now the frequency response would be L1 divided by R1. So as we go closer to the zeros, this L1 becomes smaller, which means the entire frequency response will also become smaller. As we go closer to the zeros, then we see that the particular frequency response is attenuated. As we go farther away from the zeros, then our particular frequency response value is amplified. So you should stay away from the poles and closer to the zeros if you want to attenuate a particular frequency. So if you want to, let's say, attenuate a frequency which is, let's say, 120 pi, then you should design a circuit such that there is a 0 that is closer to 120 pi, or there is a pole which is very, very far away from 120 pi. In that case, this behaves like a circuit which attenuates 120 pi. But let's say you want to pass through 120 pi. In that case, you have to design a circuit such that there is a pole which is closer to 120 pi and zeros are farther away from 120 pi. So as long as the poles are closer to a particular frequency and the zeros are farther from that frequency will be amplified. So if somebody gives you a pole 0 plot like this, and asks if it is a high pass filter or a low pass filter, all you have to do is check what is this length. Let us call this length as some L1, this length as some R1, and this length as some R2. Find L1 R1 times R2. This is equal to the magnitude of the frequency response. Just by geometrically computing this, you can say what would be the frequency response of this particular system. So if you want to know what happens at this particular frequency, then what you do, then you compute this distance, multiply it with this distance, and take a ratio with this distance. So this will be now L1, this is R1, this is R2. So as you can clearly see here, this behaves like a low pass filter. Why does it behave like a low pass filter? Because almost L1 and R2 are of the same length. Okay, so they almost always get cancelled out. The only thing that is remaining is R1. So R1 keeps increasing as the frequency increases and R2 decreases as frequency increases. Because this is the pole, this is the behavior of a low pass filter. So I don't know anything about the system. All I know is that there are two poles here and there is a 0 here. Just by looking at this, we were now able to say that this system, which corresponds to an ordinary differential equation, which corresponds to a circuit, will behave like a low pass filter. Without knowing anything, just by looking at this plot, we were able to comment about this frequency response. This is the power of pole 0 plots.